Hello, my name is Stefan Hodes and I am working as a developer relations engineer for AMD. In this presentation, I will talk to you about variable rate shading, or in short VRS. I will explain how it works and why it's a good idea to support this feature in your next title. I will also introduce you to our new technique FidelityFX variable shading, which will help you to get started utilizing this new feature. DirectX 12 Ultimate introduces several new hardware features for developers to play with. Hardware accelerated ray tracing, mesh shaders, sampler feedback, and last but not least, variable rate shading. Our latest GPU architecture, RDNA 2, which is featured in our new Radeon RX 6000 series of graphics cards, supports all of those features. And while the first three features allow the development of new approaches how your rendering pipeline works, VRS is a pure performance feature. The goal of variable rate shading is to save GPU work where it doesn't result in a significant benefit to visual quality. Doing so can help you achieve a higher and more constant frame rate, or alternatively, allow you to spend more GPU cycles on other tasks in your pipeline that will have a more significant impact on the final frame. The basic idea behind VRS is that games today are usually being played at high resolutions like 1080p, 1440p or even 4K. The higher the resolution, the smaller the pixels are on screen, and that means single pixels have a smaller impact on the final frame. Also, as resolution increases, the distance in world space and in texture space between whatever is being displayed in adjacent pixels gets smaller. As a result of this, we can expect the color of adjacent pixels to become more similar with higher resolution, at least if the pixels are belonging to the same polygon. Post-processing effects like anti-aliasing, depth of field or motion blur further reduce the color difference between adjacent pixels, and finally many games use FidelityFX cast to restore sharpness lost in those post-processing steps. All of this means that we don't necessarily need to compute every single pixel to generate the full frame in good quality. For some pixels it might be enough to assume that they have a similar color to the pixels surrounding them. Actually, some games already take advantage of this by implementing dynamic resolution scaling, which is a great technique to achieve higher and more constant frame rates, but it can also cause noticeable artifacts, which we would like to avoid. Before we look into how to integrate VRS into your engine, let me first explain how it works. To do so, we'll first take a look at how rasterization works on the GPU, and then I will show you how VRS changes that. On the right side you see an 8x8 pixel segment of the screen. The markers in the middle of each pixel are the sample locations, and the purple lines indicate 2x2 blocks or quads, as those will determine how many pixel shader threads will get launched. Whenever you render a triangle, the hardware determines how many quads contain at least one sample location inside the triangle. Then for each of those quads, 4 pixel shader threads will get launched. Threads which correspond to pixels which have a sample location outside the primitive will get marked as inactive. Once the pixel shader finishes executing, every active thread writes their result out to the pixel corresponding to it. In our case, the triangle has a size of 27 pixels, but to shade the triangle we had to launch 40 pixel shader threads, since the 27 pixels are distributed over 10 different quads. With VRS enabled, and for the purpose of this example we'll assume a 2x2 shading rate, each block of 2x2 pixels forms a coarse pixel, again having the sample location at the center of the coarse pixel. Since shading will happen at 2x2 pixel blocks, a quad is now 4x4 pixels in size. Only one pixel shader thread will get launched per coarse pixel, and the result will get written out to all pixels covered by the primitive. If you think of the coarse pixels as pixels and the actual pixels as fragments, the setup is similar to a 4x MSAA setup, except that here the grid is regular, not rotated. When we render the same triangle again, we see that the triangle covers pixels from all 4 quads. So we'll have to launch 16 pixel shader threads, out of which 10 are active. Once the pixel shader finishes executing, the 10 values will get written out to the same 27 pixels as before. Since geometric detail at the primitive edges gets preserved and our triangle is single color, the final result is identical to the previous example. One thing to note, you see in the graph on the right side that some sample locations of our pixel shader are outside the primitive. I marked them in orange. We can't have this, since this can cause significant visual artifacts, So let's quickly fix this by using centroid interpolation. Like so. Looking much better now. All in all, we managed to render the same triangle with just running 16 pixel shader threads compared to 40 before. Assuming our render path is being pixel shader bound, this is a nice saving. Now let's take a look at how to select which shading rates should be used. VRS defines multiple ways to do this, grouped into two tiers. Tier 1 only supports setting a shading rate per draw call. This provides a quick way to integrate VRS, but the control is very coarse, especially if you think about instance objects or engines where a large part of the level gets rendered with a single draw call. Things get more interesting when looking at Tier 2, which is fully supported by RDNA2 based GPUs. Tier 2 defines two additional ways of selecting shading rates. An engine can export SV shading rate from the vertex or geometry shader to determine shading rate on a per primitive basis. This way, lower shading rate could, for example, be selected for parts of an object that are far away, close to the screen edges, or having a normal which is close to being perpendicular to the view direction. This could also be used by artists to manually define which primitive requires lower shading rate than others. Finally, and this is the option I found most useful to integrate, it is possible to generate an R8 image defining in screen space which shading rate should be used on a per tile basis. On RDNA2 based hardware, one tile means an 8x8 pixel region, which is very fine-grained and allows very detailed control over which shading rate to use. The advantage of this is that this way the shading rate can be modified even within a primitive based on factors like are some pixels in dark shadow, will they get blurred, distorted by refraction or blended with a particle system or the UI, so using reduced shading rate won't be noticeable. As you see, there's lots of cases where reduced shading rate may be applied. So I encourage you to play with the different options to try and save as much GPU time as possible. You can even combine all three ways by using a combiner tree. When initializing VRS, you need to query hardware capabilities to figure out if Tier 2 is supported, and if so, what the tile size of the hardware is. Your code will need to be able to handle all cases in order to get your VRS code working correctly on all hardware. Additionally, there's a flag indicating if additional shading rates are supported. On RDNA2 based GPUs, this is not the case, since our test showed using additional shading rates are likely to cause noticeable artifacts at the resolutions currently used for gaming. Also, analyzing an image to determine if additional shading rates can be applied significantly increases the runtime of the shader, most of the time resulting in a net loss in overall performance. One final note, when using image-based VRS on RDNA2 based hardware, we copy the shading rate image into the H-tile metadata of the depth buffer when the VRS image is getting bound. This means a slight overhead, which can also be seen in Radeon GPU Profiler, but it has the advantage that the H-tile information needs to be read by the GPU anyway when the primitive gets rasterized, so we avoid having to read a second surface. However, this means you should try to reduce the number of times a VRS image gets bound per frame. When you want to disable the usage of VRS for a couple of draw calls, for example when rendering alpha testing, you should avoid unbinding the VRS image and rebinding it later in the frame, but instead use the combiner tree to ignore the VRS image. Okay, this concludes the first part of the presentation, the introduction to VRS. What you should take away from this part of the presentation and keep in mind when working with VRS is that first of all, VRS preserves the triangle edges, so it does not cause additional aliasing artifacts. Secondly, since VRS only affects the pixel shader execution rate, the depth stencil operations, which happen before the pixel shader, are always working at full precision. This means if you read the depth buffer with VRS enabled and compare it to the depth value of the primitive which you get passed to the pixel shader, for example when rendering decals, you might see some offset due to the different sample position and differences in interpolation. Third, as depth stencil is not affected by VRS, it should be obvious that using VRS in depth-only passes does not provide any gain. Likewise, if the bottleneck in a render pass is not the pixel shader, but for example the fill rate, which is often the case with deferred shading, you won't see any benefit from turning on VRS, so forward shading renderers are expected to show better gains from VRS. Obviously, VRS does not work with compute passes either. You could benefit from VRS in your post-processing if you use a pixel shader based approach, but note that since geometry edges are preserved, you might have to process multiple different pixels in one thread when you try this, similar to deferred shading with MSAA enabled. The next takeaway is that VRS works best with large triangles. If your triangles only cover a handful of pixels on average, VRS probably won't be able to reduce the number of pixel shader waves launched in a significant way. And lastly, remember to use centroid interpolation. This sample demonstrates the use of FidelityFX variable shading. As you can see, it shows a hunger scene running at 1080p and the forward rendering path runs at around 2.1 milliseconds per frame. If we force 2x2 VRS everywhere, we can see performance improve significantly to around 1.3 milliseconds per frame, but the visual quality is noticeably reduced. We don't want that, so let's disable it again. If instead we enable image-based VRS, we can see performance improves by almost 10% compared to rendering without VRS, without impacting visual quality. Let's enable the overlay to check where VRS is getting applied. In the overlay, red is bad, indicating a 1x1 shading rate, while green indicates the optimal 2x2 shading rate. Yellow and orange indicate 2x1 and 1x2 rates respectively. We can see 2x2 VRS is mainly being applied in dark, relatively uniform areas of the screen. At the bottom of the screen, there's a relatively large area where 2x1 VRS is being used. If we disable the overlay, we can see there's horizontal stripes in screen space causing this. Finally, let's take a look at the impact of the motion vectors. You see, once the ship starts moving, 2x2 shading rate is getting applied to most of it. If we stop the animation, we see this is due to the motion vectors. Let's rewind the scene a bit and look at the ship flying without the overlay. When disabling VRS, we see the difference is hardly noticeable. This concludes the sample. Back to the presentation. So, what do you have to do to implement VRS into your title? Actually, the API is fairly simple, and to further ease integration, FidelityFX variable shading provides a shader and easy-to-use interface to add VRS support to your engine. Also, the sample contains a class which serves as a blueprint for the code required to get VRS integrated. The first thing you need to do if you want to use VRS is to query hardware details. Not all hardware supports VRS. Some hardware, like all RDNA 2-based GPUs, will only support 2x2 shading rate, while other GPUs may support shading rates up to 4x4. And finally, some hardware does not support image-based VRS at all. For hardware that does support image-based VRS, you have to query the tile size of the VRS image, which, as mentioned previously, is 8x8 on RDNA 2-based GPUs. You can find all the relevant code for this in the file ffx variable shading code.cpp in the functions onCreate. The function onCreate window size dependent resources contains the code to actually create the surface for the VRS image. Once everything is set up, a couple of steps need to be taken to actually enable VRS. FidelityFX variable shading mainly focuses on image-based VRS. For this, a compute shader needs to get executed, which writes the VRS rate image. The shader takes the previous frame's backbuffer as input and a map containing motion vectors. Using motion vectors is not strictly required, since for some engines it may introduce a significant overhead to generate a motion map before the actual render path starts. But using motion vectors is highly recommended, since it significantly improves the precision of the VRS image, and as a result the quality of the final image rendered using VRS. The next step is to bind the VRS image and to actually enable VRS. To do this, you need to set the base shading rate and the combiners to enable the usage of the information specified in the VRS image. Again, the functions that implement this behavior are listed on the slide and can be found in the sample in the file ffx variable shading code.cpp. I also highly advise to support rendering the VRS image as an overlay, which visualizes where on the screen which VRS rate is being used. This is very helpful for debugging and tweaking the parameters of the VRS image computation code. The code for this is pretty straightforward and can also be taken from the sample. It's just a single draw call rendering a single full screen triangle. The draw call only takes the VRS image as an input and the constant buffer used in the compute shader generating it. Now let's take a closer look at the FidelityFX variable shading header file. This file contains the actual effect. It consists of two parts, some C code to assist with integrating the effect and some HLSL source which needs to be included into a header file that implements some bits and pieces to get it ready to work. On the C side, the file defines a constant buffer and three functions. The constant buffer contains width and height of the back buffer, the tile size of the hardware and two parameters. The first one is variance cutoff. It defines a threshold at which luminance variance within a tile is deemed acceptable to use reduced shading rate. The second one is motion factor, which defines how strongly the length of a motion vector should affect the shading rate being used. The first function, divide rounding up, is just an internal helper function which does what it says. The second function, getVRSImageRateDescriptor, returns the resource descriptor for the VRS image and needs to be called with the width and height of the render target as well as the tile size of the hardware. And the third function, getDispatchInfo, returns the number of thread groups for the dispatch of the VRS image generation and needs to be provided with a constant buffer that will also be passed to the shader, and the information if the shader should take additional shading rates into account. On the HLSL side, the code defines the same constant buffer and two compute shaders, one taking additional shading rates into account and one limited to standard shading rates. The shader supporting additional shading rates is a bit more complex. It has to evaluate more pixels and consider more options for shading rates to use. Which shader gets used can be selected by the optional definition of FFX variable shading additional shading rates at compile time. Also FFX variable shading tile size needs to be defined. Both shaders support tile sizes of 8, 16 and 32 pixels squared. Both versions of the shader use the functions readLuminance and readMotionVectors, which are only defined and not implemented. Those need to be provided by the title using the effect. On this slide you see the shader generating the VRS image in the sample. It defines a UAV, which is the VRS shading rate surface the shader is writing, two textures, one containing the previous frame's color and one containing the motion vectors, and two functions. The first one reads the color map and computes the luminance. In some cases, additional computations like linearizing the color values or modifying the luminance with values for specular intensity or depth may yield better results. The other function reads the motion vectors and converts them into texel space. If you don't want to use motion vectors, just return 0 in this function. How does the technique actually work? In a nutshell, every thread computes the difference in luminance between the pixels inside a 2x2 pixel region to determine if the difference in luminance is small enough to allow a reduction in shading rate. Those values are then compared across all threads working on the same tile to determine the shading rate applicable for the whole tile. The reason for luminance being used is simply because it proves sufficient and it's less computationally intensive than comparing full 3-channel RGB values. Actually, the shader does not just compare values within a 2x2 pixel region, it instead compares pixels with a pixel outside the 2x2 region. The reasoning behind this is that if the previous frame used, for example, a 2x2 shading rate, there's a good chance that all 4 pixels have the same color value just because VRS was used in the last frame. That way the 2x2 VRS rate would kind of burn in. Using motion vectors somewhat helps with this, but it does not prevent this effect completely. So to avoid this, we have to take comparison values outside the coarse pixel region. The motion vectors have a dual purpose in this shader. Firstly, they are used to offset the position of the color values being read. Secondly, the length of the motion vector is used to reduce the luminance variance value, which will result in coarser shading rates being used on objects that move faster relative to the camera. I previously mentioned the shading rate image overlay and how I suggest to implement it for debugging and tuning the VRS parameters. The relevant code for this is in the sample and it's located in the file vrsoverlay.hlsl. It contains a vertex and pixel shader that renders a full screen triangle displaying the VRS image. To integrate this into your code, you simply need to build a pipeline using the shader, bind the VRS image as a texture and the constant buffer used for generating the VRS image, and then issue a single draw call for a triangle, no vertex or index buffer required. So much for the technology behind FidelityFX variable shading. But how does it look in a real game in motion? Here's a video that was kindly provided by Codemasters showing Dirt 5 and how it makes use of VRS. The game looks absolutely beautiful, and you can see this is despite VRS being enabled in large parts of the frame. Thanks to the fast motion, it is not really noticeable that VRS is enabled, even on parts of the screen that barely move relative to the camera, like the player's car or the sky. Before I finish the presentation, let me point out some caveats. Please note that since VRS saves GPU time by reducing the number of pixel shader threads being launched, it will not provide any performance gain when used with depth-only parsers, compute parsers, or parsers that are fitrate bound. There's also a couple of features that effectively disable VRS. Please avoid using depth export or post-depth coverage, as well as raster ordered views or 16x anti-aliasing when using VRS, as usage of those features will revert shading rate to 1:1. Also, in addition to the VRS image generation taking some time, please keep in mind that binding and unbinding the VRS image incurs some overhead, so please try to reduce the number of times the VRS image gets bound or unbound per frame to an absolute minimum. To sum this up, VRS is a new and easy to integrate technique which can help you save significant amounts of GPU time without noticeably reducing visual quality. It works by reducing the number of pixel shader threads being launched, but it fully preserves the triangle edges and depth buffer, as those are important details contributing significantly to the final image quality. Our experiments showed that, especially at very high resolutions, 2:2 is the ideal shading rate to balance performance and quality, and it can be applied to large parts of the screen, depending on the scene and title of course, especially if the camera is moving. FidelityFX variable shading provides a ready-to-use technique to easily enable VRS usage in any title or engine. I would like to point out that FidelityFX variable shading is available at GPU Open, released with full source code. Thank you for watching.